Hello everybody, and welcome to today's webinar. Before we get started, just want to point a couple things out here. First of all, I want to introduce you guys to our team here today. My name is Nick Piotrowski, and I will be presenting this webinar. I'm a technical project leader here at Associated Research, and I run a team of applications engineers for dealing with customer issues as well as new product development. Assisting me today with questions will be Ryan Fink, who's a territory sales manager. Ryan's been with the company for almost 10 years, and he knows a lot about this equipment. He's very knowledgeable, and he'll be able to assist you with any questions you might have. If we get a lot of the same type of question, generally what tends to happen is Ryan will jump in and ask that question in front of the whole group because it would benefit everybody at that point. And then, of course, we have Mr. Jim Kennessy, who is our marketing communications leader and who is our host today. So with that being said, let's get to it. Today's webinar is Hipot Testing 101. So we're going to go over the basics and talk about Hipot testing. What is it? How do you run these tests? And we'll go over some applications as well. So a couple webinar notes before we get started. You're going to notice some utilities with the GoToMeeting bar. There is a Q&A utility that you can use to ask questions about the material being presented. So if you don't understand something I'm talking about or have a general question, use the Q&A utility and Ryan will be able to help you out with that. Any questions related to the running of the webinar, for example, if you're having audio problems or visual problems, you can't see the slide, something along those lines, use the chat utility and address those to Jim Kennessy, and he will be able to help you out with that. The webinar is being recorded and will be available in a few days on our webinar archive on our website. If you want a copy of the presentation itself, let Jim know. Email him, jimk@asresearch.com, and he'll be able to send you a copy of this presentation. It's great for training purposes, especially if you have new people who are just getting into this. So that being said, let's get into it. I'm going to do a quick recap. For any of you that attended last month's webinar presented by Syed Abidi, one of our applications engineers, we talked about electrical safety testing circuit theory. And we did a review of all of the common electrical safety tests, which included the Hipot, ground bond or ground continuity, line leakage and insulation resistance testing. Then we talked about what part of the product is tested during each test. So we had some circuit diagrams. We went over the theory of what's happening during each of these electrical safety tests. And then we also talked about the method and the order in which these tests should be run. We also went over some of the circuits for each safety test, and then we talked about arc detection and smart GFI circuits, which are unique to our instrumentation. There are other instruments out there that have similar types of circuits, but this is how we refer to ours. So if you didn't get a chance, I highly recommend you go back to our website. You can go to the website and go to the webinar archive, and you can watch any of the webinars we've done over the past year. I think we keep a record of the last 12 to 14 webinars on the website at all times. So I would highly recommend that, especially after today, because this will give you a basis, and I feel like after Hipot Testing 101, the EST would be a good follow-up to this webinar. Today, with Hipot Testing 101, here are our learning objectives. First of all, we want to understand the Hipot test. What is it? Why is it called a Hipot test? What's the purpose of this test? And what exactly is tested when you run the Hipot test? Then we're going to go over some Hipot testing requirements. We're going to talk about the AC Hipot test and the DC Hipot test. They are not necessarily equivalent, and I think it's very important to understand those differences. And I also want to go over some test parameters. Now, obviously, the instrumentation that I will be showing during this webinar is our instrumentation. So if you have Hipot testers from other manufacturers, it might not translate directly, but I think you'll get the idea. Most of Hipot testers that I've dealt with, whether it's ours or a competitor's or somebody who made one themselves, they have very similar parameters set up. So a lot of that information will translate over. So regardless of whose Hipot tester you own, hopefully it's ours, but regardless of whose you own, I think this will still be very valuable information for you. And then we're going to get into some Hipot test considerations and failures. I want to talk about leakage current and dielectric breakdown, and also arc detection. I know we talked about that in the last webinar, but I think it's important to go over again. What I want to talk about specifically in that section are the failure detectors on our instrumentation. You can receive multiple different types of failures. Hipot testers nowadays, especially the digital ones, they aren't the simple no-go testers that used to be around where it just gave you a blinking light when something failed. You actually get leakage current measurements, and they give you status indicators as well. So you could have many different types of failures, and each one of those failures can mean a different thing. So it's important to know what you're dealing with and what exactly failed. Did the failure mean your product broke down, or did it simply mean you have higher leakage current readings? Or did you just have some high-frequency noise going on when you ran the test and you got an arc failure instead of an actual failure? These things can be very handy for troubleshooting. So let's start out here and talk about the Hipot test. What is it? The dielectric voltage withstand test is another common name for the Hipot test. The reason we call it that, well, we are stressing the dielectric of a material or the insulation, and we are seeing if it can withstand that voltage drop across it, or is it going to break down. So it's a high potential test, thus the term Hipot. So Hipot is just short for high potential, but if you're going through a product safety standard and you're new to this type of thing and you see dielectric voltage withstand test and the requirements in your standard, it's the same thing. We're talking about the same thing here. So this is the most common type of electrical safety test. If you're manufacturing an electronic product, chances are you've either run this test or you are currently running this test, or you're going to be running this test if you're looking at a new product. And it's designed to verify that the insulation of the product is adequate enough to withstand high voltage. Why high voltage? You might ask yourself, well, if I have a 120 volt product, why do I need to pump 1200 volts into it? One of the main reasons that this is laid out in so many different standards is because of our modern power grid. Anything that is plugged into the wall is subject to transients that can occur on the power grid. That could be due to a lightning strike. It could be due to large equipment in a factory across the street starting up. What can happen is you get these spikes in voltage called transients that are very short-lived, but they exist on the line nonetheless. What that means is anything you plug into the wall could be exposed to these types of transients, and the insulation of a product has to be able to handle that to make sure it does not pose a shock hazard to the user. Most of the time I'm talking about type 2, or cat 2 I should say, meaning category 2, something that usually will plug right into the wall. So that's really where a lot of this stems from. And we want to make sure that the insulation is valid so that when you plug it in and you use it, it doesn't pose that shock hazard. So let's look at a Hipot test and see what's going on here. Now this diagram shows a basic circuit of a Hipot test. What we have there is an image of one of our Omnia multifunctional testers, and this is how you would connect it up for a Hipot test. So what you have here is a deliberate application of high potential between the current carrying conductors and any exposed dead metal. Now if you look at the diagram, you'll see on the bottom right hand side where those connections are, you have that whitish connection with the red around it. That would be the high voltage. So what I'm representing there is a high voltage connection going out to the product. And the reason I have two lines there is I'm simulating or showing a simulation of the line and neutral conductors of a 3-prong cord shorted together, because that's what you're going to do. And what you're going to do is apply the high voltage there, and then you'll see on the bottom coming out of the Omnia instrument there's a black connection. That is what we would call the return point. So the return point in this case is connected to what we would say is the dead metal chassis of the product, a grounded chassis in this particular case. So we would be dealing with a class 1 product, and we'll get into that more a little later. But we're going to apply the high voltage, and there's going to be leakage current flowing through the insulation of the product back to this ground plane or the return point. We want to measure that. We want to know how much leakage current is there. Is it excessive? Did we get a breakdown? So if we're looking at this, this is what we would consider to be a pass condition. So you can see we've applied the high voltage, and you see leakage current flowing through back to the return. Now you'll notice I have a couple capacitors connected from what is considered to be the DUT circuit to the chassis, two in fact. And what I'm representing there is the fact that there is a capacitance between each of the lines and the ground plane, and there's going to be leakage current flowing through both of those. I know it doesn't show it in the animation, but in reality that's probably really what's happening. You're going to get this leakage current flowing through the insulation, and you're measuring it back on the return. So quality insulation does not allow excess leakage current to flow to a product surface. What we're kind of wanting to know there is if I were to walk up and let's just say this laptop and touch this laptop, how much leakage current could I be exposed to if one of these transients occurred? Would the insulation be strong enough to handle it? And on the flip side of that, what happens if we get a failure? And this is simulating a Hipot test fail condition. This insulation breakdown results in excessive leakage to the chassis of the DUT, which can pose a shock hazard. So this would be a case where the insulation has failed, it's been breached, and now the insulation ceases to act as an insulator, and it now acts as a conductor. The material probably, in many cases that I've seen, it became carbonized, and now it's conductive, and now it's a danger. So poor insulation will break down, and dangerous leakage current can flow to the surface of a product. These are exactly the types of defects that a Hipot test is designed to catch. But they aren't the only ones. A lot of people don't realize, just because you get in the mindset of just testing a specific product, unless of course you're part of a testing laboratory, then you've probably run this in many different ways. But a Hipot test is a very versatile test. It's more than just a go, no-go test. It can find various insulation problems. Just to name a few, let's just say workmanship defects, like a scrape, maybe a tool scraped during construction, and that caused a weak point in the insulation. A pinhole. For example, say you're doing cable extrusion and some air bubbles formed in the insulation and they create little pinholes in the insulation. Hipot test can pick that out as well. Spacing. What I mean by spacing is improper spacing with respect to a grounding plane. What if you have an exposed conductor internally on your product that's too close to the chassis? Well, if you run high voltage through that, what's going to happen is you're going to have a little gap. So let's just say here's your product chassis and here's that exposed conductor. If you run the voltage high enough, air is an insulator, and the voltage will jump that gap and let you know, hey, I got a breakdown or I got a short. Something internally might not be properly spaced. You may also use this type of test for what we call our clearance distances. And a clearance distance is a distance between two conductive points internally on a product. Oftentimes when you're running tests for clearance distances, you run a Hipot test to see if you meet your clearance requirements, because a Hipot voltage will jump a specific air gap. For example, it's usually about 1,000 volts for every millimeter. So say you're supposed to have a 4 millimeter gap, you run a 4,000 volt test and it fails, well, that's telling you you have less than 4 millimeters. Now, of course, things like elevation have to be taken into account, humidity, things of this nature. This is generally laid out in product standards, and I don't want to get into too much detail on that, but it can be used for things like that as well. Heat obviously can affect the quality of insulation. Moisture, as I mentioned, humidity, or just moisture buildup inside of the insulation. You might get water beads, things of that nature. Air gaps in the insulation as well. That's the Hipot test is designed to catch that. Also material buildup. What I mean by material buildup is sometimes there are environments that cause particulates to build up on an insulation. Well, if you run a Hipot test will catch this, because you're most likely going to create a short between your 2 points, your high voltage and your return, as a result of these particulates. The voltage will jump from particle to particle, from high voltage to return, and give you a breakdown. Oftentimes, I will see something along these lines. Say I run a Hipot test, and it fails. And we run another Hipot test, and then it magically passes. And this can cause puzzlement when you're running the test. But oftentimes what happens with this is the Hipot test actually burned the material away, and now that material's gone, and the insulation is actually fine. It wasn't bad insulation, it was actually material buildup. So these are various things that can happen in a manufacturing environment. The Hipot test can catch many of these problems. So I just wanted to get across the point that don't get into the mindset that you're just going to be testing a gap of insulation or from your line neutral to your ground space. You can use this test in many different ways. Let me just throw out one more example. Material testing. We have quite a few customers that want to make sure that they don't have any holes in, let's just say, a plastic film that goes on a food product. Well, You don't have to subject that film to a Hipot test. It's not required. It's not like the film is being used in the product that's plugged into the wall where it could pose a shock hazard. But at the same time, they want to use it because you can catch microscopic holes that you would never be able to see by eye. So it's pretty versatile in that respect. So I'm going to do a quick video demonstration here of a Hipot test. So bear with me here as I get the video queued up. Now what I'm showing here, and what you're going to see, let me just make sure that this is muted so I can talk through it, is this is actually me in a video setting up a DC Hipot test, setting up various parameters. Then I'm going to connect the instrument and make a test on the product. So what I have here is a DCW or DC Hipot test, and I'm going through the various parameters. So you can see I have 1.5 kV set with a 3,000 microamp high limit. And now I'm going to step through and make sure I have all my steps good to go. So I have an AC Hipot test first. That's memory 1, step 1, as you can see on the screen there. And then I set up a DC Hipot test second. So what I'm going to use here are various leads to set up this Hipot test. We have our red high voltage lead. We have a couple black return leads. I'm also going to use one of those black return leads as a continuity check. And then we have our adapter box, which can be used instead of the leads if you have a 3-prong product. So I'm plugging in my return lead first. By the way, this is our Hipot 3 instrument. I believe this is a 3765, which is AC/DC. There's our high voltage lead. And I believe in this case, I'm also going to plug in my continuity check lead. And this is to make sure we have a proper grounding path. So real quick, I'm going to pause this video. That green light right there, what's that showing is I have my continuity check lead connected to the ground pin of my product and the return connected to the chassis of my product. And I'm just making sure, just as a quick gut check, is my chassis connected to my ground pin to make sure the product is grounded. That green light you see in the video is telling me, yes, in fact, it is, and I'm going to do that test before I run my Hipot test. You need to make sure you have a good grounding circuit before you go ahead and apply high voltage. So that's what I did right there. That's my quick little gut check to make sure that everything's good to go. So here I have a little motor, and you see I have the line neutral shorted, and I'm going to plug my high voltage, or clip my high voltage rather, right to the line neutral shorted of that motor, so my current carrying conductors, and I'm going to put the return directly on the chassis. Alternately, if I have a 3-prong terminated product, all I'm going to do is plug it into the adapter box, and then the same as before, put the return right on the chassis. Really quick, I just want to point out, the reason you're only making one connection there is that adapter box, the line neutral of that adapter box are actually shorted in the adapter box. So that goes back to the high voltage of the instrument, and that's the same on many of our testers. We short the line neutral, and then the ground pin is connected to the continuity check, as I briefly explained before. And then, of course, we have our return point on the chassis. So it's the exact same circuit. It's just a matter of how you want to connect it, what's easier for you. Most people opt to use the adapter box from what I've seen, because most of the products that I've seen tested terminate in 3 prongs. But if you don't, you can obviously always use the high voltage and return leads instead. So we have our 2 different setups here. This is if I wanted to go ahead and check continuity. You see that green pin right there for grounding. And then I'm going to put it in a DUT enclosure to make sure it's safe. And then I'm going to run my 2 tests. And you can see we ran our AC Hipot. Go to our results. We got some very small amounts of leakage current, well within our limits. We ran our tests, and it was good. So that's a brief example of a Hipot test that I wanted to run over with you guys. So now that you saw that video and have a little bit better of a feel from when we looked at the circuit of what's happening and actually looking at a Hipot test, is to talk about leakage current and what's happening. So the best indication of dielectric breakdown is leakage current measurement significantly higher than nominal current measurement. So usually what you're going to see happen, if you have an actual product failure, you'll run your test, it fails. at a specific voltage. Let's just say you're running a 1,000-volt test and you got a failure at 1,000 volts. What can be a good trick to see if you actually have a product failure? Run that test again and see where it breaks down. Does it break down at a lower voltage? If it does, that's probably a pretty good indicator that you have an actual breakdown. If it keeps breaking down at the same voltage, you might be dealing with, as I mentioned before, a spacing issue. Because obviously, let's say you have a 2-millimeter gap and you run it up to 2,000 volts and it keeps flashing over at that point. Well, that's a good indicator. I keep failing at the same point. I might have a gap issue because it's going to break over that space at 2,000 volts every time. Or if it keeps getting, if I'm failing at a consistently lower voltage with each consecutive test, then I know I probably actually have an actual product insulation breakdown. So the test voltage and the product being tested and the capacitance of the product can all impact your total leakage current. As I mentioned before, these days things have gotten much more analytical in the realm of Hipot testing. I've seen a lot of old school testers and they literally just had a red light on them, and if it went above the threshold of the tester, you got a red light that basically said product failure. But now people really want to measure the leakage current and see how this relates to insulation quality, and it can give you a measure of insulation quality. If you're running 10 tests on the same product, say you have 10 of the same product and you run a Hipot test on each of them, and you get 1 milliamp of leakage current on one but 10 on another, that's telling you something. That's telling you that you have a lot more leakage current and probably poorer insulation on the other one. Maybe there's a gap problem, maybe there is a defect, but it gives you the information you need to go and take a deeper look into that product and do a root cause analysis or a failure analysis to why the leakage is so much higher. Now, we had been talking about this before, and you guys saw it in the circuit diagram. When you run a Hipot test, and we've mentioned this a couple times, you're shorting the current carrying conductors and you're returning on the chassis. You may run into a situation, let's just say you're testing a medical device, and you are applying high voltage to one patient lead and you're returning on the other patient lead. The point is you're dropping your voltage across an insulation barrier. I say most of the time it's line neutral shorted, return on the chassis. That's very common, but this applies across the board of any insulation barrier. You can drop your voltage across any type of insulation barrier. And as I mentioned before, that's the beauty of the versatility of the test. But in any event, what's happening is you have a conductive plane on one side, your grounding or your return plane, and in between that, you have your insulation. So essentially what you've done, you've created a capacitor. And we're just measuring the leakage current flowing through that insulation to get a measure of it. So essentially, you're just creating a big capacitor. So you can think about it that way when you're running a Hipot test. Now, yes, there is a resistive element involved. If you were to look at a very simple Hipot circuit, as we showed in the other diagram, it's essentially a capacitor shunted by a very high resistance value, and you're getting leakage current through both sides. And the Hipot tester in most cases is measuring the total leakage through the DUT, which is the important value most of the time. You do have applications where you want other values, but here we're just talking about quality. So when we do that, it's essentially just like testing a capacitor. And you're going to get that total leakage is essentially almost the leakage as a result of your capacitive reactance when you're running an AC test, and the charging current, and then the curve as the current goes down and the capacitor charges when you're running a DC test, which we will get into in a little bit. We're going to talk about AC versus DC Hipot testing. So the question that we get probably most often is, what is my Hipot test voltage? And I always give the same answer. Well, what standard are you testing to? I hate to answer a question with a question, but that is a very important question. If you don't know what your Hipot test voltage is or what it's supposed to be, look at your product safety standard. For example, if you're testing household appliances, you're going to look at IEC or UL 60335-1 to look and see what's your Hipot testing voltage. In that standard, they specify dielectric withstand voltage testing requirements. And the voltages will vary depending on your insulation barrier. For example, is it basic insulation or is it reinforced insulation? It's going to be a different voltage depending on the type of insulation that you're dealing with. Now, unless otherwise stated by a safety standard, a good rule of thumb to calculate Hipot test voltage is 2 times nominal input voltage plus 1,000 volts. So for example, let's say the Hipot test voltage of a product that has a nominal input voltage of 120. So basically almost anything in the US here that plugs into the wall. You take 2 times 120, which gives you 240, add your 1,000, and that's how we get our 1.24 kV. Anybody who's ever used our instruments has probably seen that the default test setting that we have for every AC Hipot test is 1.24 kV, and that's why. A little bit of shameless advertising there. In some cases, safety agency requirements will say that you need very specific voltages for certain devices. For example, medical equipment, applied parts, as a result of being reinforced type insulation, could be tested at as much as 4,000 volts. I've seen Hipot test voltage requirements for certain materials and cables that go into the 100,000 volt range. If you have a cable that's rated for 63,000 volts, you better believe you're going to have to test it beyond 63,000 volts. And then, of course, it depends on if you're dealing with a Class 1 or a Class 2 product, because Class 2 products have double insulation and generally require a higher Hipot testing voltage. So the thing to remember is that the Hipot test parameters are called out for in your safety standards, and when in doubt, you can use the rule of thumb. But at the end of the day, if you get in trouble or you get audited, look back at that safety standard, and if you don't know and you have a safety agency that you work with, let's say you work with Intertech, who gives the ETL mark, or UL for the UL mark, ask them. Say, hey, look, you know, I'm new to this. I'm really not sure what I'm supposed to be testing to, and they will give you guidance, and they'll tell you, hey, this is the standard you need to test to. Let's look at this section, and we can look at test voltages. We do give consulting on that front as well. If you know what standard you're testing to, but just have a hard time reading the standard and picking out the language as to what your Hipot test voltage is, let us know. We have a copy of many, many standards, and we can give guidance on that front. There's no substitute for having the standard itself. And obviously, we can't share the standard or sections of the standard for proprietary reasons, but we can help you out and point you in the right direction, give you a Hipot test voltage, and let you know which pieces of equipment are going to work out for you. So before we get into that, I wanted to talk about this Class 1 versus Class 2 for a second, because it does make a difference. Now, what I mean by Class 1 versus Class 2 is, does it have basic insulation or reinforced double insulation on the product with regards to the chassis of the product? So right here we're looking at a Class 1 product, and the reason I know it's a Class 1 product is it has a ground pin. If you have a 3-prong cord, one of those being the ground pin, it's a Class 1 product because you have basic insulation as one mean of protection, and your other mean of protection is grounding to the source via that pin. So as I showed you in that continuity example on the motor, that ground pin is connected to the metal chassis of that product. So since you have a grounded metal chassis, that is a means of protection, and then the other means of protection is your basic insulation. So in this case, you can see, if I go by the numbers here, connection 1 is the return point plugged into the Omnia instrument. Connection 2 is the clip lead from the return on the dead metal chassis of the product. Point 3 there is plugging the high voltage lead into the Omnia, and then point 4, although it doesn't look like they're shorted, this is designed to show that you have line and neutral shorted to the high voltage lead, just like we showed in the video prior to this. Now, what if you have a Class 2 product? You say, hey, Nick, you call me up and you say, I have a product that has only 2 prongs. How do I test this? There's various methods you can use to test something like that. Like a laptop, for example, that only has 2 prongs. The reason that these products only have 2 prongs is instead of having a ground pin as a means of protection, you have a double layer of insulation. So it's a Class 2 product, then Class 2 double layer of insulation. So, well, if you don't have a dead metal chassis point, how am I going to get good conductive contact with my chassis to make sure I don't have excessive leakage current? There's various methods, but one common method I see in the standards is they tell you to take a 10 by 20 centimeter piece of foil. That could be copper foil, tin foil. The point is that it's conductive. And what you're simulating with that 10 by 20 is full hand contact, which is roughly about that size. And I see that same number thrown around in multiple standards. It's not universal, but it's very common. So you would put that foil on the chassis of the product, put your return point on that, because then you're getting a good measurement point. Another kind of example that I've seen as well, instead of foil, if you want even more conductive contact and an even better metric for measuring leakage current would be something like saline solution. Saline solution is conductive, so just imagine you're applying high voltage to your current carrying conductors, and then you're taking your product, whatever it might be, putting it in a saline solution, and you put your return into that solution. You're going to get great conductive contact because you're covering the whole surface. This is a common method I see done with solar panels. Solar panels oftentimes are fully insulated. There isn't necessarily grounding. It doesn't necessarily have a metal frame. Some do, but some do not. So they will actually submerge the entire panel in a saline solution, and they will return in that solution to see how much leakage current they're getting on the entire panel. That's another great method for running a test like this on a Class 2 product. So this is showing clip lead. Here's an example showing an adapter box. We're pretty much dealing with the same thing here. We have a continuity circuit that would connect to the ground of that adapter box, and then of course line and neutral are shorted, so when you plug in the product, your current carrying conductors are all applying the high voltage, and your chassis has the return point, as you can see on connection 3 right there. And then of course this is just a slightly different connection with a different instrument that is designed to run leakage testing as well. But I just wanted to show you guys a few examples. Leakage testing is beyond the scope of this discussion, but we will be talking about it later in the year. So just various connection diagrams showing how you can run these Hipot tests. And they all equate to the same thing. It's the same type of test, but you can run it multiple different ways. Okay? Now, I've been talking about standards as we've been going through this presentation, and I want to be sure to show you some examples of that. Keep in mind, these are just snippets of a document I created called the Standards Guide. These are not a substitute for the standard, so don't take this guide and say, oh, I have everything I need to run my test. No, these are snippets of the standard. There are a lot more tests than just dielectric withstand and electrical safety testing. That is just one small section of it, so don't think this is a substitute. Make sure you have the product safety standard as a reference. So for example, let's look at IEC/UL 60601 3rd edition. This is the electrical medical device standard. Section 8.8.3 of the standard, which would be for the type testing, specifies multiple different types of Hipot tests. You see, I say refer to tables 6 and 7. The reason I just didn't simply give a value was because there is a whole range of values depending on the input voltage of your device and the insulation barrier you're dealing with. Does it have patient leads? Does it have dual layers of insulation? These are all important questions to ask. The testing time in this standard is a 10-second ramp up, a 60-second dwell, and a 10-second ramp down, tested at 50 or 60 hertz or the DC equivalent. And we're going to be getting into AC versus DC here shortly, but DC equivalent basically being 1.414 times the AC voltage. And as you can see, the standard says no dielectric breakdown shall occur. Pretty common. Most standards don't give an actual leakage value as their pass-fail criteria. They basically just say, hey, just make sure it doesn't break down. And as you can see there, in this standard, it does say if you have a non-conductive enclosure, use the metal foil, as I just showed in that previous example. UL 1598 for luminaires shows a test voltage of 1,000 volts AC for an incandescent type bulb, or 1,000 plus 2 times rated for all others. Again, there's that formula, that rule of thumb formula that you so commonly see across standards. Again, no product breakdown or no breakdown on the insulation shall occur. Now, I mentioned this term before, and I apologize for not explaining earlier. You may or may not be familiar with the term type versus production. When I say type test, I mean more of like a research and development prototype testing to get a measure for leakage current on a product and design, as opposed to factory production testing, which is usually 100% of products that go out the door have this Hipot test done on them. So generally, type tests are longer. As you can see in the medical device standard, you're dealing with a total of an 80-second test if you include the ramp up and the ramp down, whereas factory production tests, they take into account the fact that these need to be run much more quickly. So usually what will happen is they bump up the test voltage by about 20%, but they only run it for a second to allow you to get through much more product throughout the day. I mean, you might need to run thousands of Hipot tests in the day. If everyone took 60 seconds, you'd never get enough product out the door. So in this case, it's a 1,200 volt AC test between the primary circuits and the accessible metal parts, and the test time is 1 second. And then one more quick example, as I mentioned, this standard 60335 is for household appliances. You can see there's various test voltages that are necessary for the type testing aspect of it, and a 500 VA piece of equipment is required. We're not going to get in depth on 500 VA in this one. Hipot Testing 102 is going to talk more about 500 VA, so definitely tune in next month if you need that as follow-up information. But as you can see here, Section 16.3 contains the electrical safety tests themselves, and of course the pass criteria, again, is no breakdown. They don't give a specific value on the leakage numbers. And then Annex A gives you your routine tests. So in this particular standard for the routine Hipot test, they actually do give you a number. Your leakage current limit is 5 milliamps, and if you happen to have an appliance that has a particularly high leakage current, maybe it's a very large appliance, and it just is not going to get below that 5 number, they allow you to go up to 30. So there's some criteria there that you can look at to determine if you would apply to the 5 milliamp or the 30 milliamp. But I just wanted to throw out some examples of standards. It's important to know how to read these standards, and you'll see very similar language between them if you start looking at multiple standards. But again, if you have questions on standards and you're not sure how to interpret it, you can always give us a call and we can try to point you in the right direction. So I've talked a lot about Hipot testing. What I really haven't delved into, aside from noting it, is the AC versus the DC Hipot test. So let's talk about that. Depending on the product being tested and the test standard, you may be able to perform an AC or a DC test. Some standards only allow you to do one or the other. Some standards say if it's a product that runs off of AC, you got to do an AC test. If it's a product that runs off of DC, you have to do a DC test. So be sure to pay attention to that language. But as you saw in one of my standard examples, some allow you to run AC or DC. You just have to make sure that since the AC is more stressful, that you run the DC equivalent. So both AC and DC Hipot tests have inherent advantages and disadvantages, depending on the product you're testing and what you need to do. And it's important to understand the difference between the two to know which one that you can run. Let's get into that. But before we do, we have a quick poll question for you guys. So take a look at the poll question, and then we'll discuss the results after you guys are done. We're going to take about 45 seconds to a minute to allow you to answer the question.
Okay, Nick, we had about 26% say they're performing AC Hipot, 25% performing DC Hipot, and 46% performing both, and then we had a small percentage, 3%, performing neither.
Okay. So between the AC and the DC kind of split there, and then of course you get these people who are performing both, which means that they're converting AC to DC. And thank you for sharing your results. That's pretty much what I expected. That's what I see in the field as well. And I think you're going to understand more why that happens as I go through and we start talking about what the difference is between the two. So let's look at that. Now, unfortunately, we don't have enough time here to talk about the exact ins and outs and nature of AC versus DC and all that good stuff. That would be a whole nother series of lectures if you wanted to get in depth about it. But let's take a look at these two waveforms. AC stands for alternating current. And as you can see from that image there, we have what's called a sine wave. So the AC voltage is going to fluctuate from positive to negative polarity constantly based off a specific frequency. Here in the US, 60 hertz, which means you're getting that full AC sine wave 60 times every second. So you're switching polarities. The DC waveform is consistent. It's a constant output level. So you see that blue line in the waveform, let's just say that's a 1,000-volt test. That is a 1,000-volt DC constant output. There is no flipping of polarity. So just get a general sense of those waveforms as we move through these parts of the presentation. And the behavior of the AC and DC current varies in resistive and capacitive circuits, and that's why it's so important to understand the difference when we're talking about Hipot testing. AC current is bidirectional, whereas DC flows in just one direction. right? We already saw in the waveform that we're going in both polarities on an AC sine wave constantly. So the relationship between current, voltage, and resistance is defined in the famous Ohm's law. Ohm's law is very important when we're talking about Hipot testing. So here in looking at these AC and these DC circuits, you're going to have a different relationship on how much leakage current you're going to see between the two types of tests, the AC and the DC Hipot test. So Ohm's law governs the relationship between these three values. Ohm's law, very famously, V equals IR, where voltage is equal to current, I, times resistance, R. And as you can see, you can rearrange that equation any way you see fit to get the values that you need. Now, on the left-hand side there, those two little images where it says current is bidirectional, that is showing an AC circuit. And we know that because the little circle with the sine wave in it, that's our voltage source. So that's representative of an AC voltage source. Then you can see the little arrow I is showing the direction of the current. And you can see the reason we show two circuits there is because it's flipping. And then R, the resistance, is our load. Now, when we're dealing with an AC Hipot test, the simple little resistive circuit that we showed, that's nice and everything. But as I mentioned before, with a Hipot test, you're not really talking about a straight-up resistive circuit. It's mostly a capacitance. So it's important to understand the nature of how an AC voltage is going to react with the capacitance. So the AC potential is applied across the capacitor, which in the case of running this test is an insulation barrier. The resulting leakage current that flows is 90 degrees out of phase with the applied voltage. This is if you're dealing with a pure capacitor. If you have a capacitive resistive network, which in what most cases is happening in an actual Hipot circuit, it's going to be somewhere in between 0 and 90, maybe a 45-degree shift. It really depends. And the reactance, or the current that you get, this leakage current, is what we call reactive current, is a result of the capacitor. So you're constantly, since your current is bidirectional, you're constantly charging and discharging this capacitor, and this can actually be modeled as what we call a capacitive reactance. So since you're charging and discharging the capacitor constantly and these levels are shifting, you can actually model a capacitance as a resistance, and that's what we call capacitive reactance. And you can actually use that value to calculate how much leakage current you might expect in your product. But the important thing I want you to remember here is that when you do an AC test, you're getting mostly reactive current. You're getting some resistive current, but when you run an AC Hipot test, what you're really seeing is a snapshot of the total current. It's not separating it out. You're getting some through your capacitive element, you're getting some through your resistive element, and then on the return, since you're measuring the leakage current on the return, you're getting a total leakage current value. With a DC Hipot test, it's a bit different. And if you've ever run an AC versus a DC Hipot test, you'd see this. It behaves very differently. What happens, as you can see in that graph, you get an initial spike in current. And then eventually, that current settles down as the capacitor charges. Think about a capacitor. If you're thinking about AC and DC in terms of water, think about a capacitor as a giant jug. And if you're talking about AC, think if I'm pouring water into the jug, think about the jug being constantly filled and then drained at the same rate of water. Well, the jug's never going to fill up unless you pour a lot of the water in at once. You're going to have pretty much a consistent level if you assume that the filling and the draining is the same rate. With DC, it's not the case. Remember, we talked about we're only going one direction. So you're filling the jug up with water. What's going to eventually happen? The jug's going to get full of water. Then no more current can flow. That's why when you run a DC Hipot test, you're going to see initial spike in current as the capacitor, or in our analogy, the jug fills, and then that current's going to taper off because we're filling it, and then we're going to reach a point where you really have no current flowing. It's almost an open circuit at that point. So if you've ever run a DC Hipot test, the behavior you would notice is you'd see a spike in leakage current at the very beginning, but then as the test goes on, you'll see almost no leakage current. Assuming, of course, you don't have a breakdown or a failure. You'll see almost no leakage current because the capacitor is full. No more current can flow through it. So very different behaviors here. Now, the leakage current that is measured in an AC is the vector sum of the resistive and the reactive components. That's what I was saying. You see in that little vector diagram down there, you're getting IT, or what we call the total current. And some of our testers are actually capable of separating those values out, the total versus the real. But as I mentioned with DC, what happens is, if you think about capacitor and a resistor, if that capacitor is an open circuit because you fully charged it with DC, the only path left is the resistive portion. So all you're seeing, once that capacitance charges with a DC test, all you're seeing is the real element that's left from that circuit. So that's an important distinction to make. And actually, the video demonstration I have is after this, but I wanted to talk about something really quick here. So having gone through all that information, let's talk about the advantages of each one of these. With an AC Hipot test, no ramping is required. You don't have to worry about current spikes. So if you have a really large capacitor in a DC test, and you just go ahead and apply a voltage, you might get a failure right away because you have this huge spiking current, and your Hipot tester thinks, oh man, this is so much current, this must be a failure. That might not necessarily be the case. And a way to tell is extend out your ramp up, extend it out to 10 seconds as opposed to 1 second, you might pass. The reason you failed is because you had spiking current. So one of the disadvantages of a DC test is they tend to take a little bit longer. And in a production environment, that might not be desirable. So with an AC Hipot test, you don't have to worry about that. You can do a 0.1 second ramp up and just let it run, and you're usually good to go. The other thing about an AC test that's advantageous over a DC is you don't need to discharge the device under test. We talked about discharging during our safety and electrical safety compliance 101 webinar earlier this year. If you charge up that capacitor, just like that jug we talked about, and you don't discharge it, and somebody comes up and they touch it, it's going to discharge through them. That can be dangerous. With a DC test, you have to make sure that the DUT, or the device under test, is discharged before the test ends. With an AC test, you don't have to worry about that, because remember, you're constantly filling, draining, and by the time the test is done, there is no charge left in the capacitor. The other thing is the AC test is a more stressful test, because you're testing in both polarities. So you're going positive, negative, positive, negative. So it's a better measure of the quality of your insulation. That's why if you're running the equivalent DC test, you have to multiply it by a factor of 1.414 to make sure that it's equivalent to that AC level of energy. And this is the most commonly accepted test by the agencies. Usually AC is accepted across the board, except in specific cases. The DC Hipot test advantages, you don't need a large current transformer. You don't need a large transformer because, as I mentioned, you get some spiking current, but then as it stabilizes, you have very low current values. So it's usually safer for the operator who's running the test. It's generally easier to perform on very highly capacitive DUTs because you don't have to worry about capacitive reactance. But the thing is, it's not always accepted by safety agencies. For example, the 61010 standard as a type test only allows AC for AC circuits, so you wouldn't be able to run an equivalent test. So it's very important, once again, to look at your standards. So I just wanted to lay out some advantages and disadvantages of these tests here. Now, I'm going to talk about breakdown detectors very briefly. I'm going to show you a couple examples of the various different types of failures, and then I'm going to leave it open to questions. So there's different types of failure detectors on these instruments. We have leakage measurement, as I've been talking about, which it'll measure your leakage and see if you go above a threshold that you've set. Your straight up breakdown detector, did you get an insulation breakdown, and arc detection. And each one has a priority on the instrument. Shorts and breakdowns always take precedence, and they have a very fast interrupt, 400 microseconds on our instruments. Leakage limits, they react a little bit more slowly because it's just you set a threshold on the instrument, and it's looking at the leakage current and it's seeing do you tick above that level. If you do, it's going to fail you. And that goes per the sample rate of the instrument, which the sample rate on our instrument is 100 milliseconds. So every 0.1 seconds it gets updated. And then, of course, our arc detection, which I'll show you in a minute. So let's look at a quick failure detection circuit. This is showing you all three different failure detectors we have. First of all, if you start at the very bottom there, we have our overload. That's your breakdown detector. You're looking at both frequencies. What I mean by frequencies is high frequency and low frequency. So low meaning your 50, 60 hertz standard, and then high frequencies meaning 10,000 hertz and above, which is usually indicative of a breakdown if you start getting this really high frequency noise on your circuit. Your leakage meter is just your low frequency 50, 60 hertz meter that's measuring at a slower sample rate, and your arc detection is actually looking, just like your breakdown, at your high frequency. So your arc detection is kind of looking at your high frequency only, your leakage meter, your low frequency only, your overload detectors is looking at both. The arc detector is an interesting little piece of technology. And what is it doing? Well, what it's looking at is it's looking at any frequency that's above 10,000 hertz. So you get these high frequency waves that will ride on the low frequency waves. So first we put it through a high pass filter. If it sees something greater than 10K hertz, it passes it through, and then it's going to compare that to a sensitivity level, 1 through 9 on our instruments, 9 being the most sensitive. If the amplitude of those little high frequency spikes go over the threshold setting, you're going to get an arc fail. That's how that circuit is working. So your arc settings roughly equate to milliamp trip levels, and here are your levels. So 1, you have a 20 milliamp spike, so meaning if you were going to fail with an arc level 1, you would have to have a high frequency spike that exceeds 20 milliamps, which is really high, all the way up to 9, which is a 2 milliamp spike. Okay? Now the important thing to remember with arc detection is this is not an exact science, okay? There are many variables involved with the buildup of corona and arcing, especially through a medium like a gas, like air. Humidity, temperature, elevation, these all play a part. So if you're comparing arc levels between different instruments at different sites, you're probably not going to see the same values. And the other important thing to remember with arc detection is this is generally seen as a quality issue, not pass-fail criteria. I've never seen a product standard that relied on arc detection or these types of high-frequency levels as a pass-fail criteria for your Hipot test. So usually it's just your breakdown or a higher excessive leakage current level, not your arc detection levels, but this is a good tool for quality control. Now, I promised you videos. I'll give you videos. Let's look at some of these different failure detections. And I realize we're getting close to the 1 hour mark, so I just want to show you some differences in the different failures. So here I'm going to show a breakdown. So you see I have an AC Hipot test, and what you might not see there is those aren't connected. I actually have them about 1 millimeter or 2 apart. And what I'm going to show you here is a breakdown through air. Air is an insulator, so this is actually simulating a breakdown. So they're very close together, and I'm going to run the test, and it's going to spark over through the air. So it was actually probably just over 2 millimeters because it failed at about 2.39 kV. But it knew it was a breakdown. How? It got that high frequency noise, that corona buildup in the air, and then it shorted out, indicative of a breakdown, which is what you just saw here. Now let's compare that to a short failure. What's a short failure? Well, it's just what it sounds like. We're not talking about high-frequency noise in this case. I have those leads directly clipped together. So if I just push test, we're going to get a short failure immediately. So you can see that's a little bit different of a case. What about a high-limit failure? As we mentioned, this would be what we call a leakage limit failure. So not the high frequency or the quick interrupt, but the standard 50, 60 hertz, and we're getting an excessive amount of leakage current. So to simulate that, what I did was I just have connected it up to a big capacitor. So I'm doing an AC test at 5,000 volts. So we're going to get a very low capacitive reactance, which means a lot of leakage current. And you can see it failed out pretty quick. We only got to about 290 volts before it failed out and exceeded the 50 milliamp capability of this instrument. So that was what we would call a leakage limit failure, or as you can see on this instrument, high limit T, high limit total leakage current. Finally, let's look at an arc failure, because this one's a bit different. Again, what I'm doing here, hold on, I'm going to back up a little bit so you guys can see that. What I have here is I actually have a piece of mylar, and I want to actually create a little buildup of arcing on the surface of the mylar to show the arc fail. So building up, building up, building up, and if if I had sound on this video, you'd actually hear a buzzing noise. That's the actual buildup of corona. So now the instrument read that and was able to show that there was an arc failure, but it wasn't a product failure. The mylar didn't break down. It was just a failure with regards to it seeing that buildup and then detecting that there was an issue. Okay, I know we went through a lot of information during this webinar, and hopefully this gave you good groundwork for what a Hipot test is, what it can do, and at the same time what it can't do. If you would like a copy of this presentation, contact Jim. He can give you a copy. We'll also, again, have it up on our webinar archive in the next couple days. Now, don't forget to take a look at our website. We have a wealth of resources for training materials, so take a look at our website and go to our resources section. Also, feel free to follow us on YouTube, LinkedIn, and Twitter. We give regular updates on things like these webinars, where we're going to be at with trade shows and things of that nature. Just to keep everybody in the loop here, we will be at the Product Safety Symposium, PSES 2015 in Rosemont, Illinois. We will have a booth next Monday, Tuesday, and Wednesday, which I believe is 18th, 19th, 20th. So come see us. I'll be there all 3 days. Dwayne Davis, our technical services manager, will be presenting about Hipot testing on Monday. So he'll have a full-on presentation showing some live demonstrations. And we have a booth as well that'll have some of our sales guys and myself there. So come check it out, and we hope to see you there. Thank you for attending this webinar. We really appreciate your attendance. Hopefully you find this useful. And come back next month when we have Hipot Testing 102. I'm going to leave the floor open for a few minutes for questions. So feel free to ask away. And if there's a question that we feel is relevant for the group, Ryan will chime in. But again, thank you for your attendance, and we hope to see you next time. All right, I do have a quick question here from somebody. They said they are having a problem testing several thousand-foot spool of cable, that their Hipot tester keeps failing, but there isn't an actual insulation failure. I can almost guarantee what's happening there is that you are exceeding the capacity of the Hipot tester. I don't know which tester you have, but most of our testers have a maximum of about 30, 40, 50 milliamps. And if you go beyond that, it's of course going to indicate a failure because it's assuming you have a cascade of leakage current. What's happening is you have a lot of capacitance. So every type of cable will have a capacitance per foot. And of course, multiply that out by several thousand feet, and you have a pretty high capacitance. And if you do a quick capacitive reactance calculation, you would probably calculate that your leakage current would be something in the realm of 60 to 70 milliamps for that much cable. What I would recommend to you, if you have the capability to do so, switch over to a DC Hipot test and do a long ramp up. So do a DC Hipot test. Make sure, of course, that you check your standard and that there is an equivalent DC Hipot available in that standard, but do a long, like 1 or 2 minute ramp up. Allow the capacitance to charge, and then run your test, and you might be able to get away with it. So that's something you can certainly do in the case where you have very high capacitance. Good question. All right, well, it looks like that's about it. So I will cut off the presentation. But again, thank you for attending, and we hopefully will see you at the next webinar.